All right, let's do some radical review. Um, which one should we start with? I'll start with a very basic one, just to review the idea. So here we have a question that says simplify. It's a little bit blurry, but we can still see the numbers. How do we go about doing this? Have you done this in class?
Not really.
So this is radical math, right? Even if you haven't done it in
Mm-hmm.
class, we have done it. So you want to treat this as like terms. That's the approach. You want to use the like term approach here. You can replace the radical with any letter you want. So let's say instead of 5 root 3, it was x. Let's say root 3 is x, and let's say root 6 is y. You don't have to do it like this, but this just to show you that it's very simple. So what you do is you see there's an x here, there's an x here. The final answer would be 8x plus 2y, right?
Mm-hmm.
Same idea here. The final answer is going to be 8 root 3 because those root 3's, you can treat them as x's. So these two are like terms. You can treat
Mm-hmm.
these as x's. So it'll be 8 root 3, okay, plus 2 root 6. And that's the final answer. Now, why is that the final answer? Because root 6, you can't reduce this radical any further. To be able to reduce a radical, for example, root 48, this one is reducible, this one is not. The way you know whether something is reducible or not is you want to think, can you fit a perfect square in there? Can you fit a perfect square inside the radical? So by perfect squares, I mean 1 squared. Well, 1 squared is 1, so that doesn't really count. But 2 squared, 4. 3 squared, 9. 4 squared, 16. These guys. So when you look at root 48, you want to ask yourself, can I fit any of the perfect squares in there? In other words, can I divide the number that I have here with any of the perfect squares? For this, we can, right? Because 48 is
16.
16 times what?
3.
3. And then what you do is you split these two numbers up. So this radical is just like the exponent. This exponent applies to every character inside the bracket. Same thing with the radical. That radical, that root, applies to every number inside the radical. So you can kind of like split it apart like this. And root 16 is a 4. So you'll have 4 root 3. And that's the reduced version of 48, root 48. So that one you can reduce. But root 6 you can't reduce because the smallest perfect square we have is a 4, and 6 is not divisible by 4, right?
Mm-hmm.
So that's as far as you can go. So the answer to this question is just simply one step. You just combine the root 3's. Or let's try another one. So again, you want to think whether or not the radical can be reduced. Root 3, can we reduce root 3?
No.
No, we cannot because no perfect square is divisible by root 3 or just 3. So that stays as is. Plus, what about root 20?
It goes into 4.
Goes into 4. So it'll become 3 times root 4 times root 5 minus. What
Mm-hmm.
about root 12?
That also goes into 4.
That goes into 4. So it'll be 2 root 4 root 3 and 45 is 9 times 5, right? Like that. So
Mm-hmm.
you have 4 root 3 plus root 4 is 2. 3 times 2 is 6. So this entire thing becomes 6 root 5 minus 2 times 2 is 4, 4 root 3 plus root 9 is 3, 3 root 5. And then do we have any like terms? Yes, we do. We can combine these two. So 4 minus 4 is not gone. And then we have 6 plus 3 root 5. That'll be 9 root 5 for the final answer for this question. So not too difficult, right?
Mm-hmm.
If you can reduce it, it's just adding like terms. I don't think it's super difficult. Does it get more difficult than that? No, it does not. Let's do one more. Let's do one or two more. So this one just says expand and simplify. So we have a squared. So you know what that squared means. It means you have two different brackets with the same interiors times 2 root 2 minus root 5. How do we expand this expression? Any ideas? You just FOIL it, yeah? When you have two different
Mm-hmm.
brackets, even if you have three different brackets, you just FOIL it. When I say FOIL, I'm saying you're going to take this term, you're going to multiply that into the first term in the other bracket. That's the first thing you're going to do. And then you're going to take that same term in the first bracket, multiply it with the second term in the other bracket. And once you've exhausted that, then you're going to take the second term, go this way, then second term, go with second term. So overall, there's going to be four terms in the next step. What is 2 root 2 times 2 root 2?
Does it just become 4 root 4?
Yeah, it becomes 8 minus 2 root 2 times root 5. There's an invisible 1 here. So you multiply the number outside the radical with the number, and then you multiply the radical with the radical. So here it would be 2 times 1 is a 2, and then 2 root 10. What's the
Mm-hmm.
third term?
Negative 2 root 10.
Yes. And then the last term is just 5, or square root of 25, right?
Mm-hmm.
So the answer here would simply be 8 minus 5 is a 3. And what about these? When you combine them, what do you get?
Is it just minus 4 root 10?
Yes. Can root 10 be reduced?
No.
No, it cannot be because the smallest perfect square is 4. After that, it's 9. Neither one of those two numbers can go into 10. I'll just explain you the concept of this is more of a coding terminology, but it also applies to maths. I'm explaining you what mod means. Okay, mod is an expression that we use in maths. Well, you've heard of these guys, right?
Mm-hmm.
Now, mod is more. It's a division. Here, let me just show you an example. It's kind of simple. So let's say you do 5 mod 2. Mod is just a form of division. Does 2 go into 5? Well, not exactly, but 2 goes into 4, right?
Mm-hmm.
And the remainder would be 1. So the answer to 5 mod 2 is 1. Now let's try another one. 14 mod 3. So 3 is going to go into 12. What's the remainder?
It's 2.
It's 2, right? So this is what it is. 3, you have 14 here. 3 times 4 is 12. And then you have a remainder. This is the answer to the mod, okay? It's just the
Mm-hmm.
leftover remainders. When we're doing the radical math, to reduce a radical, your mod has to be 0. You cannot have any remainders, okay? So when we think about
Mm-hmm.
72, what's a perfect square that goes into 72? 36? Does it go into it exactly? Yes, it does. So the mod there would be 0, right? 72 mod 36, the answer would be 0 because there's no remainder. And this is what you want when you want to reduce a when you want to reduce a radical. So this
Mm-hmm.
would be root 36 times root 2. So the answer would be 6 root 2. Most of these are pretty simple. Let's try some of these guys. This one, the question, all it said was simplify. What could we possibly do?
Um,
Is there anything we can do, or is that the final answer?
it's the final answer.
No, it's not. So why is that the case? Hmm, we've done this before, right? Usually, okay, if a question gives you something like this and asks you to simplify, it's not written there, but what they want you to do is to get rid of the radicals in the denominator. We don't want radicals in the denominator usually.
Mm-hmm.
So you have to get rid of the roots in the denominator. How do we get rid of those? You have to multiply it by something. And the term starts with the letter C. It's called its conjugate. So the next step here would be to multiply it by the conjugate. What's the conjugate of root 6 plus root 3?
Root 6 minus root 3.
Exactly. So you have root 6 minus root 3. Same thing in the denominator. So in the numerator, you get 2 root 6 times 2 root 3. Or you can just leave the 2 outside. I don't know which one will be better. I'm going to leave it outside. For now, just in case, we cancel the 2 with the denominator. What about the denominator? What do we get?
Don't we just get 6 minus 3?
Yeah. So you get 2 over 3 root 6 times root 3. That's it. Okay?
Mm-hmm.
So not that difficult. Just when they ask you to simplify, it's the denominator. Keep that in mind. It's the denominator you need to get rid of, not the numerator. What about this one? What do we multiply this with?
Root 6 plus root 10.
Yeah. On the denominator, we're gonna get minus 4. Tell me if you agree. Because it becomes 6 minus 10.
Mm-hmm.
So you get minus 4. What about the numerator? So you have to FOIL it, right?
So it's root 12
Yeah.
plus root 20. And then,
All right.
mm-hmm.
And then you can
Yeah.
reduce all of them. And I'm going to do this quickly because 12 is 4, 3. So this becomes 2 root 3. Plus 20 is root 4 times root 5. So that'll become 2 root 5. What about 30? Can we reduce 30? 50 we can. 50 will be 25 times 2. That'll be 5 root 2. What about root 30? Is that reducible?
No.
No, because the perfect score is 4, 9, 16. A rule of thumb is that you don't have to check for perfect squares um, for half of this. So the half of this is 15, right? So
Mm-hmm.
16, I just wrote it there, but you don't have to worry about 16 either. There's no way that will go into this. So 4 and 9 doesn't go into it, so therefore it can't be reduced.
Mm-hmm.
What about um, can root 40 be reduced?
They can.
It can because 4 is gonna go into 40. Okay.
Mm-hmm.
30 is special because 4 doesn't go into it. And that's just a review of some of the radical math that you'll be doing. First of all, what is this shape? Is it a trapezoid? Is it a trapezoid?
Yeah.
So for a trapezoid, right, the formula for the area is a plus b over 2 times h. Because this is a, this is b, doesn't matter which one you call a or b, and h is the altitude, the right angle distance between a and b. Look at what's required in a trapezoid. It has a very special requirement. What do you notice between these two lines? If this is 90 degrees, right? If you drew it like this, like how this is drawn, or if even if you drew it like this, how that's drawn, would that ever be 90 degrees?
No.
No. So in a trapezoid, the requirement is that this line A and this line B, they have to be what? They can't touch ever. Even if you extend it perpetually, they can't ever touch. What is that property called? Parallel. Okay?
Mm-hmm.
This line in a trapezoid has to be parallel. So that although this has the shape of a trapezoid, it is not a trapezoid. There's two types of trapezoids you can get. You can either get a regular trapezoid, and look at what's the difference. In a regular trapezoid, your this side length is equal to this side length. So if this is x, this is going to be x. The other type you can get is irregular. Again, these two lines have to be parallel. That's the requirement. But this line and this line doesn't necessarily have to be equal. So this is x and this is y now. Okay? That is called an
Mm-hmm.
irregular trapezoid. But again, both of these lines always have to be parallel. So that's not a trapezoid. Why do we care about that? It's just asking us for the perimeter, which is good. Because if it asks us for the area, I'm thinking, how would we even do this if it asked us for the area? We don't have enough information, I don't think, to do this. The only thing I can think of is if it asked us for the area, is we would turn this into two triangles like this, okay?
Mm-hmm.
And then you have that height for the first triangle. You have second height for this other triangle. That would be a grade 12 question. It would be you have to use, let me think what you could possibly use. You can do this using SOHCAHTOA, I think. You have to do it a few times because you have two right angle triangles. You can probably use SOHCAHTOA to find the height and find the distance and find the area. But here we're only asked the perimeter, so we don't have to worry about the area. So what's the perimeter of this shape? So you just add all those sides up. Very simple. Can root 80 be reduced? So 80, right? So 4,
It
9.
goes up to 16.
Yeah, exactly. You can either do 4 times 20. That's one option. The next option is you can do 16 times 5. One option is better than the other. Turns out you want to fit the maximum, the biggest perfect square number, the biggest square number in there. So even though both 4 and 16, they go into 80, it's better to use 16 because root 20 can be reduced further. So you'd have to
Mm-hmm.
do two reductions. If you use 4, you'd have to do it twice. So two steps, was if you use 16, it's only one step, okay?
Mm-hmm.
So we're going to do 16 times 5, so that becomes 4 root 5. What about 45? Can we reduce 45?
It goes into 9
It
5
goes into,
times.
so it'll be 3 root 5. Plus root 5 and 20 is 4 root 5, root 4 root 5, so it'll be 2 root 5. And then we pair up the like terms. Everything here is a like term. So 4 plus 3, 7, plus 1, 8, plus 2, 10. 10 root 5 would be the final answer. And you're done. Cool?
Mm-hmm.
So this one says, without using a calculator, arrange the numbers from the smallest, from greatest to least. So descending order. Let's look at the first term there. Root 3 times root 3 plus 1. What does that expand to? If we open the brackets, we have root 3 times root 3 plus 1. What does that
It's
expand to?
3 plus root 3.
3 plus root 3 is correct. So it's slightly more than 3, right? Slightly more than 3. 3 plus root 3. It's about 4-ish. What about the second term?
It's 3 minus root 3 plus root 3.
So you can think about it in terms of difference of squares. So that will give you a whole number final answer instantly if you see it. If you use the difference of squares, you will get 3 minus 1. Okay, for the second term? Yeah,
Mm-hmm.
let me show you. So for the first term, we got 3 plus root 3. So 3 plus root 3, this is about 4-ish. For the second term, you see you have a plus b, and then you have a minus b, right? So it becomes a squared minus b squared. So here it would be root 3 squared minus 1 squared. So that entire term becomes 3 minus 1, 2, okay?
Mm-hmm.
So this is about 4. This is about 2. What about this one? So the whole squares are always more annoying than the difference of squares type question. So this is going to be 1 minus root 3 times 1 minus root 3, and that is not going to be 1 minus 3, okay? There's going to be a middle
Mm,
term. Remember that. Every time there's a whole square, there's always going to be a middle term. So this, if you expand it, you're going to get 1 minus 2 root 3 plus 3. So that'll be 1 plus 3 is 4 minus 2 root 3. Cool.
mm-hmm.
So this is like 4 minus 2-ish, because root 3 is about 1 or 1.5. So this is going to be 2. It's about 2, okay? It's not about 2. It's less than 2, because this term is about 3. So this is about 3. So this is about 1. Because we can't use a calculator, that's why. And then the plus will obviously be, even without doing any math, I think that's going to be the biggest number there. Let's see. This times this. So if you expand it, you get 3 plus 1 plus 2 root 3. So that'll be about 6. So there you go. This is the biggest one, second biggest, third biggest, and the smallest. Okay, we're not doing any more radical things. Let's try doing this one. This seems very interesting. Have you heard about the Fibonacci sequence? It
Mm-hmm.
is just an order of numbers. So it goes like this. It's very unique because the first two numbers are 1 and 1, okay? For the next number, what you do is tn plus 1. The next number is tn plus tn minus 1. It's a sum of the previous two numbers. That's what Fibonacci sequence is. So what will be the next number?
2,
2. What about the next number?
3.
3, exactly. 5, 8. Okay, these were given. What about the next one?
Do you still just keep adding
You
them
just
up
keep
to
adding them. Yep.
13,
13. What about the next one?
21?
21, right? 21. And then it just goes like that. Let's graph this. I'm kind of curious on what it looks like. Let me pull up the graphing tool, which I guess these days in high school, Desmos is the most popular one. But it's not as powerful. I don't know if I've told you, Desmos is not as powerful, especially when it comes to like complicated functions. So what we're gonna do is we're gonna make a table for Fibonacci sequence. So we're gonna have a term number, okay?
Mm-hmm.
So it goes 1, 2, 3, 4. It's pretty simple. And what I can do is I can just drag this down. So those are the term numbers. And then this part is gonna be a little bit difficult. The number itself, the output. The first term number is 1. 1, 2, 3, 5, 8, 13, 21, 34. How far should we go? I don't know. 55? What's the next one? 89, right?
Mm-hmm.
Actually, let me see if this works. I would love for this to work. I have a feeling it will work. And then what you do is boom. Did that work? Yeah. Okay, boom. There we go. So we have the term, and then we have up until like the 130th term. Let's graph this. Let's see the general pattern. Ooh, what does that look like? What does this function look like? Is it a quadratic? Look at the shape.
It's exponential.
It's exponential, exactly, right? Can I add a solid line through it? Um, Let me add a trend line through this. And then what we're going to do is we're going to see if we can predict the numbers, okay? If we can predict the numbers. Let's put an exponential model there, please. Let's display the equation. So there you go. We have an equation, okay?
Mm-hmm.
So this is called modeling, basically. You have a few sample points, and then you use that sample point to come up with an equation. Now what we're going to do is we're going to use this equation to see how accurate our model is. So let's check it for some random x value. So when the term number is 25, the actual Fibonacci sequence is 75,025. Let's see how accurate that is. So I'm going to use this, okay? The formula that we just got from Excel. So all you have to do is 0.45 if it writes 0.45 times e to the 0.4811 times, I'm looking for this, okay? 25, like that. Let me plug that in a calculator and let's see. So I got 75,281.696. What do you think about this result? Is it accurate? It's somewhat accurate. It's not precise, right?
Mm-hmm.
But it's within a couple of hundreds, which is not that bad. Why is it not perfectly the exact same number? Why is there a discrepancy between what we got and the actual answer? Because you see this sequence here?
Mm-hmm.
You can't quite model this specific pattern using a modeled equation like the one that we have here. But what we could do is try using this formula. Let's try using this one. This question is asking us to find F2. We're not going to find F2. We're going to find F25. Let's see if that gives us a closer approximation. Um, where are the ends? So there's only two ends. So all you have to do in this equation is replace both of those ends with 25. 1 minus root 5 over 2 to the power of 25. Let me plug this in. Would be a good experiment. 1 plus root 5 divided by 2 to the power of 25 divided by root 5 minus 1 over root 5 times 1 minus root 5 over 2 to the power of 25. I got exactly 75,025. So that's the difference. Using a modeled equation, you're not going to be precise because the modeled equation only uses a sample of points or a handful of sample points. Now, if we had the entire Fibonacci sequence, right? If we had it all the way to, let me type, why am I drawing? Exit draw. So if we had the Fibonacci sequence, still drawing, all the way to infinity, okay? Let's say over here, this keeps going on. and then we have the infinite term number, and then the term itself at infinity. Let's say we had this. And we used all of these points to model the data. And again, it would spit out an equation like this. That equation would give you the precise answer of 75,025. It's because it's used every single data point in the sequence, right? Is that
Mm-hmm.
practical? Obviously not. Even in real life, we never use um, that many points because every point in a data collection means an increased cost. Every data point that you collect has a cost attributed to it, cost and time, I guess I should say. So after a while, there's a lot of diminishing returns. In terms of a plot, okay, let's see if we can come up with a plot. So this is the quality of data. And then over here you have the data points collected. Kind of looks like this. Or you can say quality of your study as well. After a certain number of data points, right? Look at what happens. What do you call this? What's the trend? What's the curve doing there? So it's like kind of like plateauing, right? Like a square root function.
Mm-hmm.
Yeah. So in other words, right, what's the technical definition of this? The slope, what is it starting to become? What is it
Zero.
approaching? Exactly. The slope is approaching zero. So all that means is there is a certain number of data point which we will call n, okay? This is called the size of your sample or sample size. How many data points do you have? After you cross this point, this area is called the region of diminishing returns. And this happens in almost anything that you can think of. Think of it in terms of science, you can think of it in terms of sports, in terms of eating. After a while, okay, you're gonna start seeing diminishing returns. So it's not worth spending money on getting these data. Okay?
Mm-hmm.
So let's say every data point here costs you, so this is before, this is for less than n, and then we're gonna do greater than n. So let's say there's a cost, there's a time, and there is the efficiency. So any point less than n, let's say the cost is $1, the time, let's say it takes you 1 hour, and the efficiency is, let's say, 0.9. Greater than n, your dollar value is going to increase, your t is also going to increase, and your efficiency is going to decrease. Okay? So that's
Mm-hmm.
why in statistics, usually we don't consider this region. That's why the example I gave you earlier, if we had all data points up until infinity, we would have a perfect model. But the thing is, we will never do this because that's not practical at all. So yeah, a little bit of a tangent there. But there you go. There is a formula that exists called Binet's formula that will give you the precise answer for the nth term of a Fibonacci sequence. All right, here we have a rectangle. Is that a square or a rectangle? So the side lengths are different. It's a rectangle. All right, so how do we find the area of this rectangle?
We just multiply
So let's do
the
it.
two
So
sides.
2 root 3 times 4 root 2 times root 3. That's very simple, you'll see. What's 2 root 2 times 4 root 2? 2 root
8
3
root 6.
times. 8 root 6 is correct. Can root 6 be reduced?
No,
No. What about 2 root 3 times root 3?
it's 6.
Yes. So that's the final answer. Done. The perimeter, well, you just multiply the two side lengths by 2, right?
Mm-hmm.
Or you add them to themselves. So like that. So you get 4 root 3. Again, this is very simple. 8 root 2 minus 2 root 3. So the answer will be 2 root 3 plus 8 root 2. That's it. Very simple. Let's look at the next one when we consider this shape. What is this shape called? Is it a pyramid? No, it's not a pyramid.
Mm-hmm. Like a rectangular prism?
Yeah, it's a rectangular prism. We have been asked to find the volume. How do you find the volume of a rectangular prism?
Length times width times height.
Yep. So I'm going to multiply these two first because I can use difference of squares. So look at this. A plus b, a minus b becomes what? A squared minus b squared, right? So it becomes 5 root 2 squared minus 2 root 3 squared. What does this evaluate to? 5 root 2 whole squared.
50.
50. 50 is right. On the other side, you have 12, right?
Mm-hmm.
4 times 3. So that is 38. So we just multiply 38 with root 15 minus root 2. Can root 15 be reduced?
No.
No. So that's it. That's the final answer. Pretty simple, right?
Mm-hmm.
If a rectangle has an area, so there's a rectangle. Let's call this x. Let's call this y. So we know that x times y is 4. The area is 4. Or we can even call it L times W. So that's one point. The next point, and it has a width of root 7 minus root 5. So we actually know the width. The width is root 7 minus root 5. So in other words, you take your length, you multiply with the width, okay, like that, you get 4. Length times width is 4. Question says, what is the length in the simplest radical form? All right, how do we do this one? So we're trying to solve for L, right? We need to get rid of this bracket. How do we get rid of this bracket?
You divide.
Yeah, you divide. Now the question is this the final answer?
No.
What do we need to do?
You multiply it by root 7 plus root 5.
Exactly. It's called rationalizing the denominator. You multiply it by the conjugate. Then root 7 plus root 5 So in the numerator, you'll get 4 root 7 plus root 5. In the denominator, you will get something else. What do you get in the denominator?
Just 7 minus 5.
Yeah, so you just get a 2. So 2 goes into 4 twice, so the final answer here could be 2 root 7 plus root 5. Cool?
Mm-hmm.
That's it. Not that difficult. Cube root is the same thing. Most of them you need a calculator, except I guess up until 5, it's not that bad. What's 4 cubed?
64.
Yeah. So some of them just remember. 3 cubed is the most popular one, I think, and 2 cubed. The other ones you can just use a calculator to find it. All right. Express the ratio of the area of the larger circle to the area of the smaller circle in simplest radical form. Cool. What is given? What are these numbers?
The radius.
Yeah, so we have the big radius, we have the small radius. So let's find the area of the big circle. What's the area? Area of a circle is pi, what?
R squared.
R squared. So pi 2 plus root 3 squared. Area of a smaller circle is pi times 2 minus root 3 squared, right?
Mm-hmm.
And they're asking us for the ratio, so you're going to do area big divided by area small. In the numerator, you'll have pi times, I'm trying to do this, 2 times 2, 4 root 3 plus 3. So when you FOIL it, by the way, I'm using this formula here to open the bracket. And then if there's a
Mm-hmm.
minus, it just becomes a squared minus 2ab plus b squared. So that goes in the numerator. In the denominator, you have the same thing, except the middle term, there's going to be a minus. Now, let's see what cancels out. Pi is gone. 4 plus 3 is a 7. 4 plus 3 is also a 7. So we have 7 plus 4 root 3 on the top and 7 minus 4 root 3 on the bottom. Is that the final answer?
You have to rationalize.
You have to rationalize it. So what do we multiply it by? So the conjugate, right, will be 7 plus 4 root 3. Okay?
Mm-hmm.
So if it was root A, it's going to be root A. If it's 3 root A, it's going to be 3 root A. That doesn't change. If it's 3 root A plus B, then it becomes minus B. So if there's multiple terms, if there's a sum or a difference of terms, you kind of have to think about it with respect to difference of squares. That's why you always multiply it by the opposite sign. And the new denominator takes precedence. So minus here means the conjugate is going to have a plus there, so that we can do difference of squares in the denominator to get rid of the radical.
Mm-hmm.
So here in the numerator, again, I'm just going to use that formula to be 49 plus 7 times 4 is 28, 56 root 3 plus 16 times 3, 48. In the denominator, we get 49 minus 4 times 3. Oh, sorry. 49 minus 16 times 3, 48. So the final answer here is what? 97 plus 56 root 3 divided by 1 or divided by nothing, and we're done. So not that complicated of a question. You just have to know how to open square brackets, which again, at almost grade 12 level, that's not terribly difficult. Okay, let's talk about this one. Is this always true, sometimes true, or never true? Let's think about the number, okay? If A was 0, if B was 0, would that statement be true? Or would it not be true?
It would.
It would. So A zeros check out. What about when A is 1 and B is 1? Does that check out?
Yeah.
No, it does not. 1 plus 1 is root 2 on the left-hand side. On the right-hand side, you get 1 plus 1, you get a 2, right? Do you agree?
Mm-hmm.
So is this true?
It's not.
It's not. So it only works. That statement is only true, and you can double check this using other numbers. That statement is only true when A and B are 0. Okay?
Mm-hmm.
And then for everything else, so when A and B are not 0, it's false. You can write it like this. And when A and B are 0, it's true. And that will be the answer. Cool?
Mm-hmm.
All right, let's call it there for today.
Okay. Thank you.
See ya.